So yes, I'm going to talk about traffic control and how to use it on Linux and in containers to test applications. First, who am I? Work on the Rocket container runtime in the last month, and I'm currently tech lead. A couple of years ago, I worked on traffic control for a different use case for a multimedia application in cars. In this presentation, I will first explain what is traffic control, what it is for, and why it could be useful for tests. I will do a demo first in Rocket without Kubernetes, and then after that I will do a demo in Kubernetes. I will talk about what I would like to have on my wish list, what I would like to have in Kubernetes, and to test traffic control, to test application with traffic controls. So to start with, what is traffic control? How does it work on Linux? So traffic control can be used for different things. In this example, we have a web server sending data over the internet to different clients. We can use traffic control for different things, for a fair distribution of bandwidth, to make sure that one client doesn't starve and doesn't get any contents compared to the other clients. We can use it to reserve some bandwidth for some specific application. If you have multiple kind of traffic like DNS, HTTP, SSH, or UDP, we can set some policies to decide how to share that. And we can use traffic control to avoid buffer bloat, to make sure that the buffers in the routers on internet don't get too much data, and it causes problem with latency. So on Linux, to set up traffic control, we use queuing discipline. That's something you configure on the network interface on ETH0, for example. And each queuing discipline can decide what network algorithm to apply, and that algorithm will decide which packet to emit next when there is some free space on the network interface to send something. So when to send the next packet and which packet to send next. Queuing discipline is something which can be configured at runtime on Linux. We can change the configuration. It doesn't need to be configured when the interface, network interface starts. There is a tool called TC for traffic control, which can control the network traffic, and it's also called shaping, network shaping. It uses behind the scene netlink sockets to communicate with the kernels and set up the queuing discipline. There are several queuing disciplines. The default one on Linux is very simple. It's first in, first out, basically. And the first packet being emitted is the first one being sent as soon as possible. This default queuing discipline actually have several bands. So there is a basic priority systems. Depending on the content of the IP header of each packet, depending on the type of service, it will place the packet in one of the three bands. And then it will always take the next packet from the first band, if there is something, the highest priority band, and then go to the next one. There are other queuing disciplines. I will not go too much over them. Like this one is doing a round robin to make sure that the distribution of bandwidth is a bit more fair. And this one is the default one since set up by systemd. So when the Linux distribution starts and systemd starts, systemd will select this one as a default. So every new network interface, if it is not configured otherwise, will have this fair queuing control delay queuing discipline. Okay, but that's a few queuing discipline. What can we do with that for testings? So there is another queuing discipline called netem for network emulator. And when installing this one on a network interface, we can set up some different properties. We can change the bandwidth. We can say we don't want more than 10 kilobits per second or more or less on that interface. We can change the latency. We can add some milliseconds or some seconds of latency. we can configure that network interface to lose some packets, like 3% or 1% on corrupt, and there is a lot of other options to choose the probability method to drop packets or to duplicate packets, etc. So that's the queuing discipline I will focus on in this presentation. We want to use that in containers because when we develop an application and we want to test it, we don't want to change the network configuration of the host computer on my laptop. And the queuing discipline is a property of each network interface. So if a container has a network interface, we configure the queuing discipline on that network interface, and it doesn't change anything else on the other network interface on the host. In this example, that's what I would like to have. I would like to have a testing framework which is able to configure the queuing discipline on different containers. And I can choose to have the network emulator queuing discipline with some property, some limit of bandwidth, for example, and have different properties on other containers. Here in this example, I show the egress traffic going out from the interface. It could be nice to change the properties of the traffic both for ingress traffic and egress traffic. It's a lot easier to configure the queuing discipline on the egress traffic because it's a lot easier to decide what we emit next rather than decide what other people send to us. But it's still possible to do something on the ingress traffic. There is a way to buffer the incoming packet with a virtual network interface called IFB for intermediate functional block. And we can use traffic control to redirect all the ingress traffic to a network interface to that IFB 0, and then send it back. So from the point of view of that network interface, the traffic here will be egress, so we can add a queuing discipline and set up it as we want. I will come to my first demo. What I would like to demo is to have a container running with Rocket with a media server. The media server is just a RTP server, RTP/RTSP server. So RTP is a protocol to serve media files over UDP, and RTSP is to control the it's a control channel using TCP. And RTP is supposed to, that protocol is supposed to be okay enough when there is a packet drop. When some UDP packets are lost, it should work. But actually, do all implementation work correctly? That's something which would be good to test. And some testing scenarios like this one are a lot easier to test if you can change the network configuration. So I will run Rocket on with a media server on a container and on the host a media player. So let me try this. So here I have I'm just starting Rocket with a script to it's an image based on Alban Linux, I think, with VLC as a media server, and then I will configure it to start to serve one specific file. Okay, and then I will start the video. So it will connect to that the port exposed by the Rocket container, and I will stream a bit in the middle of the video. And meanwhile, I will start an application which is a very simple GTK JavaScript application where I can configure the queuing discipline. So let me go back to that video. So here we can see, okay, it seems to work fine. There is no good network condition between my container and my host. But what if I change the network condition? Like if I set up 1% packet loss, we will probably see some problems on the video. Seems to work still okay, but what if we had 3% loss? it's not so great, but that's expected. And when, that's not so good. But if I set it back to 0%, hopefully it will come back correctly. Yeah, the next time there is a keyframe in the video, it works fine again. So I can use that to test media server. There is still some problem. Yeah. If I add some delay, doesn't change that much. It's a bit freezing sometimes. And if I put a small delay, maybe it will come back, or maybe not. So that's useful to test. So usually developers have a good networking condition. They have a fast internet, and, or they develop things locally, so they don't tend to notice every problem. But when we actually have bad network conditions, that's when we can start seeing problems. So that was this demo. The video was Elephant Dreams, which is on Creative Commons. And all the demos I'm doing are, you can try them yourself. The steps to reproduce the demo are on this address. I will show it back later. So how it works, I have this application running on the host, and it joins the network namespace of the container. So when this application is in the network namespace of the container, I can configure that network interface and change the properties of the queuing discipline. I would like to do a demo in Kubernetes as well. What are the things I would like to test in Kubernetes? So that's example of Kubernetes cluster with 2 nodes, with some pods on each node, and each pod can communicate to all the other pods on the Kubernetes cluster. And I want to have a testing framework which is able to configure in real time the network condition of each pod. So I would like to say that, for example, this pod over there has limited connectivity. And if I can define a network scenario where at the beginning it works fine, and then I have some latency, that would be good. How I did that, I implemented a small daemon called TCD for traffic control daemon. It accepts commands either over dbus or gRPC. With Kubernetes, I'm using gRPC, so it accepts external commands to install a queuing discipline on a pod or a container, and then configure egress or ingress on them. TCD is available at this address. And then I'm using a with scope to have a view on my containers. So with scope is provide a web UI where I can see the state of the pods and containers in Kubernetes. And that web server is provided by a scope app. And scope app can communicate with a scope probe. There is one scope probe on each node. It's installed as a daemon set in Kubernetes. And there is one TCD on each node. I set it up as a daemon set as well. And I added some patch on with scope to add some buttons here to change the properties of the queuing discipline network emulator on the specified pod. So I will start a demo with that. So I have a cluster on my laptop. It's started with Vagrant on CoreOS. It's using CoreOS Linux, and I started simple pod. It's just a script. You can see a part of the script here. It's sleep 2 seconds, and every 2 seconds it downloads a file from internet, and I actually connect from with scope attached to it to see what it does. and I see it's downloading every 2 seconds a very small file, and it's quite good networking condition. It downloads the file in less than 1 second, so that's quite good. But what if I click on this button to change the speed of the network? It will just add some latency. I clicked, and it's become a bit slower. It downloads the file in 1 second. If I add something like, I think, 1 second of latency between each packet on ingress, it will become even more slower. So I can change the configuration of the network interface from this web UI. I can put it back to fast, and hopefully the next time it downloads, it will be fast again. So I'm going to use that for a more complex application than just a ping or download over the network. I installed the guestbook example from the Kubernetes Git repository, and it's a simple guestbook. So here at the moment I have good networking conditions, so I don't see any problem. It seems to work fine. I'm adding messages in my guestbook. It works fine. But what happens if I change the network condition? So I'm not sure if it is this one or the other one. Let me try. Make it a bit slower, and I will refresh the page. Okay, maybe it was I didn't click on the wrong one, on the correct one. Okay, now it's a bit slower to load. And if I reload the page again, you see the message disappear and appear again. So what if I put it even more higher latency? And reload. It takes some time. And then my message disappeared, and it looks like all my data disappeared. Okay, actually my data is back. So what happened is we have user interface problem. The guestbook seems to say to the user, okay, there is no data in the guestbook, everything disappeared, but it's just quite slow. So when we have this kind of web UI, we want to provide useful feedback to the user. And for that, I patched the PHP application to have the same guestbook. I will show it from here. So here I have 2 front ends to the same Redis backend. And on this one, it should work better. So if I add a new message, here there is some feedback to the user that is loading. If I configure that front end much lower, and I'll go back here, I will reload the page. So it's quite slow now. And it's loading, and the user has feedback that is loading. So that's quite good to test a web interface during slow networks. But that's kind of still manual. I have to configure manually the latency and then change it. So it will be good to have a framework to do that. There exists some, you can use Selenium to do automatic tests without having to click on the web UI manually. And there is other frameworks that I will show now. I have some codes running Agouti. And it's a Go code looking like that, where I can describe each step. So first I'm going to a specific web page, and then I'm waiting that the HTML page contains some HTML element. And then I'm adding some message, and then waiting until it's fully sent. So let me find this. So here I have some file. That's the same code I put on the slide, where I will send a message, good morning, with a date. And when I run this, in this demo, it's not using Selenium directly. It will start Chrome and download it. So since I configured the queuing discipline as with a high latency, it takes some time. But here I test that the loading message appear, and then I add some message is being sent, and it's still sending. And after some time, it will be updated, and then the test work with success. So that's something which is difficult to test if you cannot change the traffic control rules, if you cannot add some latency. Because if I go back to the to here and I configure it as a fast network in normal conditions, maybe the test will not have time to notice the loading message. So it might work, it might not work. Okay, here it works, but sometimes it doesn't work. Here it doesn't work. So if we want to check that the message appear correctly, that's useful to change the properties of the network. That's the last demo, but I kind of have a wish list of things things I would like to have to be able to test more complex scenarios. So for example, in these demos, I only have one queuing discipline, netem, installed on the network interface. But sometimes I have a different kind of traffics, like HTTP to this IP address, or HTTP to that other IP address, or DNS, or something else. And all of this traffic go to the same queuing discipline with the same properties, in this example with some latency and 2% packet drop. But it will be useful to say, for example, that the SSH traffic doesn't have latency, but the HTTP traffic with some latency. It's possible to do that. It's possible to install several queuing disciplines on the same network interface. So the queuing discipline we have seen so far, that a network emulator and FIFO and the basic one are classless queuing discipline. But there are some classful queuing discipline. What it means is we can classify the packets in different class. You can apply some filters to say, okay, this filter with destination port 80 go to this class, and then with this queuing discipline with these properties. But some other packets with a different destination ports will go to another class. And I can put a different queuing discipline with a different latency. I think that would be nice for some scenarios where I want to restrict the connectivity to a pod, but not in the same way for every destination. So if this pod emits some traffic to this, I want this latency. And if it emits some packets to another pod, I want different latency. So for that, I need to classify the packet depending on the content of the packet, depending on the IP destination of the packet. There is a filter for that called U32. What it does is apply a mask on the packet, and for every packet emitted on the network interface, the filter will apply a specific mask and decide on that how to classify the packet. I think that would be nice to use for testing some algorithm, like the Raft consensus algorithm used by etcd. If I want to test how etcd cluster behave with some specific asymmetric conditions, like for example with this node, the connectivity between this and this is quite high, it's 5 seconds, and it's quite higher than the election timeout. So what happens in this condition, I would expect that this node get excluded, but I've not tested it, so I don't know. Another way, another thing I would like to have is to filter by application. So on Kubernetes, when we have one pod with several apps, all the applications in the pod are running within the same network namespace. We have one network namespace per pod. When we use RocketNetis, with Rocket, each application in the pod are started by systemd unit, And I would like to be able to say that application has some properties with some latency, which is different from this one. But actually, since all the applications in the pod are running in the same network namespace, they have the same network interface, and they have the same queuing discipline. But there is some C groups called net class, which can be used to filter by application, which are on different C groups. Systemd used to have an option for that. It was removed, but it's still possible to use the C group API directly. Okay, I will skip that. There is a more complex way which can be used to filter packets. In this example, we can write some code in C language or a subset of the C language, and it can be compiled to the BPF architecture, which is kind of virtual machine. It's not a real architecture, and then that code can be uploaded to the kernel to configure the traffic control on the network interface. And then the kernel will execute that code for every packet sent by that network interface. So in this case, we can basically write any algorithm we want. We are not restricted by the previous way of classifying packets. So it's done with BPF and with BPF system calls. And with the new BPF, there is a way to share some hash table. They call it extended BPF map. And that map is just a hash table which can be accessed by the classifier, by the code which will be executed for every packet. So you can keep some statistics up to date here, or use that map to classify the packets. And then userland application can access this map, this hash table, to check, to read what happened, to check the statistics. So I think if we generate some statistics this way, and the testing framework can access it, then we can have a lot of expressing power in the testing framework. So if you remember that Go code to test the guestbook application, I could write condition based on statistics generated in this way. That's all. So all the demos I've done, you can try them yourself. And the slides are available online, and you can check the source. Before the questions? Yes?
Can you go back to the slide? Yeah.
This one?
At the end, to check the link.
Okay.
And the slides will get posted. And I'll make him tweet out the slides. Are there questions? Do you want to add?
I wanted to say something. It's not a question.
Go say
Oh, yeah.
something.
I just wanted to say that the scope stuff that you were showing, I work for Weedworks. If you want to see more about that, I'll be talking this afternoon about that from Tom.
Good.
Quick question. So this looks great, and I love what you're doing. How easy would it be to translate it to Docker and Docker containers?
So the demo I've done in Kubernetes are actually with Docker. So in the way, if I go back to, this, TCD can accept commands on gRPC, and I can both say, okay, use this Docker container, or use this Rocket container, or use this systemd nspawn container, and it accepts a different way of specifying which container I want to modify. I would like to, so this demo on Kubernetes was done with Docker. I would like to make it work with Rocket as well. It will require some updates in scope to be able to support that.
How easy would it be to plug in the TCD APIs, like to basically have something like Chaos Monkey but for network network packet loss inside your own cluster. How easy do you think it will be to like move it to like a cluster level thing where you can say like now randomly assign packet losses across pods of this particular namespace or this particular label?
Sorry, I've not heard everything. Do you want to change randomly the properties, or?
So let's say that you wanted to like apply like packet loss across like all pods of a given label or a given namespace, and basically simulate like chaos monkey like network packet loss inside your own cluster.
Right. So far, TCD is kind of demoware. There is not much methods. It has 3 methods: one to install the qdisc and one to set up the properties on ingress and egress. But I would like to improve that. But behind the scene, it uses netem, and netem has commands that you can use to make some temporary change. You can say, okay, drop the next 1,000 packets, but then go back to normal. And we can a testing framework will request connect to all the TCD on all the nodes, and to tell of them, okay, change everything on every pod. That will be possible to do.
Just a quick question on, have you taken this to the next step and actually investigated if you can use this as a traffic shaping framework in itself rather than as a testing tool?
No, so I've seen there is some code in Kubernetes to do the traffic shaping, but what I wanted to do is to focus on changing that dynamically for testing needs. So I've not looked into a way to configure statically shaping the traffic in Kubernetes.
Okay.
Yes.
How easy would it be to adapt the framework so that it would work not just for containers, but maybe just in general as a traffic shaping? So I guess certainly not for general network, but also for testing purposes, but not necessarily for containers. Is it possible to do that as well, or not at this point?
Yes, if I go back to I would like to be able to filter the traffic by pods. With systemd, when you start a service, you can say this service is starting in a new network namespace, and it doesn't by itself set up the connectivity with outside, but you could add that connectivity, and then it will basically like a container. Otherwise, if you don't want to use any new network namespace and running only on the host, then I would like to have that as a way to set up different rules for every systemd service. Systemd doesn't expose that API anymore, but the reason it doesn't expose it is it was using the net class cgroup subsystem, which works on a non-unified hierarchy, which is a cgroup version 1, but the cgroup version 2 doesn't have that net class cgroup subsystem anymore, but there will be new things to replace that. So it's kind of something in a move in the kernel. Yes?
That's something in my mind. Could you filter? Okay. Is it possible to filter or pin the failure properties per client, so you could simulate multiple clients with different properties at the same time and test concurrency bugs, from that point of view? So in a use case, you have 4,000 mobile users,
yes,
and say 40 of them are behind different types of broken networks. So you would have various customers who experience differently broken network behavior at the same time. Can you simulate that, or set that kind of setup up?
You would like to distinguish each connection to the same process, and some of them be good and some of them be bad.
Yes.
more difficult to do because when you decide which connection is good or bad, you will need to have your application sending that the list of connections and setting up a filter based on that. And it will work for the egress traffic fine. For the ingress traffic, it's more difficult because on the Linux network stack, the incoming traffic comes first, and then we apply some traffic control rules, and it's only later than it's routed to socket, a specific socket. So at that time, we apply the traffic control. We don't know yet which socket and which application will receive the packet, and there is some contract rules, but it's difficult to do.
So, as a follow-up, if you could just randomly pin a certain fraction of your test clients to just experience different jitter per client, and then pin that jittering behavior per client once it has been assigned, would that be possible?
Sorry, I'm not sure to understand the question.
So, think about it. If you have a random fleet of customers, and some of them will have network broken in different ways. So you would have one network with bad latency, some with packet drops, some with horrible repeats and packet replays. And once you assigned, if you have 1,000 test users and you want to have 200 of them being broken in different ways, then you randomly assign 200 broken customers, and then would assign broken behavior per customer, keep that behavior of that particular customer for the test suite. Would that be possible?
I guess it will be possible, but yeah, it will be more invasive on the process to send the list of connections. I've not tried that.
So it's tricky. Okay.
Yeah.
But it's doable. It's tricky.
So when you have the interface of the container, does TCD actually add the ingress interface filtering as well, or do you need to like pre-configure the container to have the additional ingress interface to do the netem on ingress?
You can configure it after. So that's. Do you mean configuring that? Yes. You can configure it after. I guess when you configure it, there might be a couple of milliseconds where it might not work, but I guess that will be fine. And in my demo, when I click on the buttons in with scope to change that, I actually installed that IV thing after the container has been started.
Can you talk a little bit more about the BPF stuff? Are you using the BPF compiler collection, or are you using Clang? Have you written any kind of libraries, header files that would assist in writing unit tests? Or is that basically just a vision at this point?
No, it was just in my wish list of things I would like to add, but I don't have code for that.
Maybe to answer the gentleman in the front about having a test case where you would have random behavior for a subset of customers and keep that behavior. The way to do that is you would use a traffic generator and then have multiple TCU32 rules to match on like subnets, and then have a net emulator enforcing the behavior you want per subnet that would keep that behavior for your ranges of customers. So you could have customer sets with like a random chit, some with packet loss, some with random delays. So netem would allow you to do that. I'm not sure if your TCD allows for that sort of configuration yet, but it's definitely possible to use it.
Yes, for now TCD is basically like I guess a couple hundred of lines of code, so it almost have nothing. So it just have enough to do this demo, but yeah, that will be possible to add more.
Any more questions?
Why was the net class support removed from systemd, and what's the future plan there?
So because the net class cgroup subsystem is something available on cgroup version 1, the non-unified cgroup hierarchy. but in unified cgroup hierarchy, the cgroup version 2, that subsystem doesn't exist anymore. And the reason for that, the reason that the kernel people didn't put it there, is it's not really a hierarchical thing, and it doesn't make delegation really possible in a safe way. So, and the reason systemd removed that support is they don't want to have some options which will actually only work on cgroup version 1, but not on cgroup version 2. And they want to have API, systemd API, which works for the future, and they are going towards the cgroup unified hierarchy. There are another way of filtering based on cgroups, which is not the net class cgroup subsystem. There is a patch from a couple of weeks ago in the kernel to add a classifying method based on the full path of the cgroup, rather than just a number like it was before. But it's kind of same thing moving, and it's still not fully there yet. But still, if you use the non-unified cgroup, the hierarchy, the net class cgroup subsystem is still there, so you can still access it directly without using systemd.
We should probably wrap up.
I have.
Put your last slide up again, so for the video folks watching this later, they'll have all those links. Of course, you're hired. Everybody's hired. Perfect. Thank you very much, Alban.
Thank you.